Hello, Physics Land. This series of lectures is on circuits. Hopefully, by the end of it, you might understand a little bit more about like how your house is wired or things along those lines. You won't be an electrician, mind you, but you'll have at least a better understanding of how it works. The first lecture we're going to do is an intro to electricity as well as circuits. As always, you need 3 or more bullet points worth of notes and a 1 to 2 sentence summary, though to be honest, it'll probably be a few more than 3 bullet points for this one. So in this first lecture, we're going to answer what is electricity, why does it flow, and when does it flow? So asking the question, what is electricity, is a lot like asking, what is a river? It's not just water, it's the idea of the flow of water, or really the flow of any liquid, whether it's water or magma in this case. A river is that idea of flow. Now, I bring that up because similarly, electricity is flow. It's specifically the flow of charge. So just like how a river isn't just water, it's the flow of water, the electricity is not just charge, it's the flow of charge. Now, when I talk about charge, we have charge all around us, but only when it moves do we call it electricity and does it behave in a unique and different way. Now, to talk about where that charge comes from and when it flows, let's take a quick aside and talk about atoms. The basic building blocks of the things around us. So you think about like all of the things around us, they're made up of different molecules, and if you break apart those molecules are made up of different atoms, and an atom is the kind of elemental building block of the materials in our universe. Now, if you actually zoom into an atom or break it apart further, it stops behaving the same way. But if we look further in it, each and every atom is actually made up of 3 types of particles, and just different amounts and combinations of those particles. Those 3 particles are protons, neutrons, and electrons. And we bring this up because they are the source of charge. Now, protons have a positive electrical charge and are at the center of an atom. And they determine what element something is, just so you remember. So the difference between carbon and gold is just the number of protons. In that center area is also neutrons, and they have a neutral charge. So you can think of it as 0, but I like to think of it more as a balanced charge. It's not positive, it's not negative, it's just kind of balanced at neutral. And neutrons help kind of glue the stuff together. So they help keep the protons here together in the center. And all of those things combined in the center make up what we call the nucleus. And the nucleus, the reason why we're calling attention to it, even though it has charge in it, the nucleus tends not to change. And when it does, we call that a nuclear reaction, which is usually something more dramatic than what we're going to be talking about with just electricity. So this isn't going to be the source of our charge, even though it is, or has some charge in it. So we need to talk about the last piece, which are electrons on the outside. Now, electrons, we say they orbit around the nucleus, kind of like planets around the sun. It's not really an orbit like that, but you can take chemistry and learn more about that. But these electrons have an orbit of sorts, or an orbital, around the nucleus, so they're kind of moving around. And these ones on the outside shell, so you see how there are different shells or orbits here, the ones on the outside shell are the ones that tend to move around the most. Specifically, they can actually move from atom to atom or molecule to molecule. And so when atoms combine, it's those electrons on the valence shell that are either coming or going, so being added and subtracted. So electrons on the outside, they can change. Stuff in the middle, nucleus, it can't change. Well, it doesn't change as often. It can. And so when we talk about electricity and we're talking about the flow of charge, we're going to be talking about the flow of these electrons on the outside. So electricity is just the movement of charge. It tends to be electrons. It doesn't technically have to be, but it tends to be electrons. So that's our first question. Now, when we talk about electricity, there are 3 terms we're going to talk about a lot: electric current, voltage, and resistance. So just a quick intro to those. Current is the flow of charge, represented by the variable I, and it's measured in amps. Voltage is the amount of energy per charge, more on that later, represented by the variable V and measured in volts. And resistance is how hard it is for electricity to flow, represented by the variable R, and the units are ohms. So, answering that next question, why do electrons flow or why do they move? We are going to go back and look at our river example here. So, you think about the river, the reason why it flows is because water is going to go from an area of more gravitational potential energy to an area of less gravitational potential energy. By having a difference there, we enable a flow to happen. Similarly, by having a difference in electrical potential energy, we enable electrons to flow from an area of more electric potential energy to an area of less electric potential energy. So, why do those electrons flow, or what creates that electric potential energy? Well, before we talk about that, let's talk about some properties of electrical charge. Kind of like magnets, but not the same thing as magnets. Like charges will repel, much like magnets will repel. And so it can be two positives or two negatives, and they'll repel each other or push apart from each other. Opposite charges will attract. So instead of pushing apart, they come together. And so a positive and a negative will attract each other. If there's no charge, there's no force. So if we think about, let's say, two spheres, so just a giant metal sphere, and one happens to be negatively charged and one happens to be positively charged. If we place an electron, remember an electron's negative, in the middle, think about it for a second. What direction is the force on that electron? All right, so hopefully you realize that if this is negative and this is negative, they're going to repel, so it pushes it to the right. But if this is positive and this is negative, these two will attract, so again, it will be pushed and pulled to the right-hand side. And so that's the direction of the force on it. So by having that electron here in the middle, and because it's being attracted and repelled and pushed and pulled, etc., we are actually storing energy in its location right here. As it gets pushed or pulled that way, it releases some energy. That electric potential energy turns into kinetic energy in this case. So now I want you to think about what would happen if instead of, for example, we had a medium amount of charge here. What if we had a lesser amount of charge? What if there was less charge on each sphere? What would happen to the force on the electron? All right, so hopefully you realize that if there is less charge, it will be a less force. They kind of go together. This also means there's less energy released as it gets pushed and pulled towards this way. And so that's really what's going on when we're talking about the flow of electricity. It's really the flow of electrons. They're being pushed and pulled, and as a result, they release energy along the way. So if we had, for example, more charge on our sphere, it would be a bigger force and therefore more energy stored. Well, this idea of the kind of amount of energy that the electron has based on kind of the setup is the idea of voltage. It really just describes how much energy does the electron have to release to other things. So when we talk about why do electrons move, when we look at like batteries or other things, it has a positive side and a negative side. And you can think of it as like a buildup of negative charge on the negative side that's pushing electrons through the wires and through the circuit towards the positive side, or the positive side's attracting it. So electrons move because there's a buildup of charge. And they're all like built up together and repelling and pushing, and they just want to escape. There's kind of a pressure of sorts. And that pressure, that buildup of charge pushes them or pulls them through the circuit. And that's why they move. Now, formally, you would actually describe this as the buildup of charge creates an electric field that pushes or pulls the electrons through the circuit, but that goes into the idea of electric fields that we'll talk later about. One last piece about this is obviously electrons can move more easily through certain materials than others. So you think about the electrons are moving through the wire here, but they're not like jumping out and going in random directions. So the things that allow electrons to kind of move easily or freely are called conductors, and things that tend to hold on to electrons, so you think about those valence electrons, they're called insulators. They don't allow electrons to move quite as easily or freely. A little comparison between the two: conductors allow electrons to move or flow easily between atoms. It only has 1 to 3 valence electrons, those ones on the outside. And some examples of good conductors are gold, silver, copper, aluminum. Insulators are things that don't allow the electrons to flow as well. They tend to have 5 to 8 valence electrons on that outside shell. And some examples are like glass, quartz, plastics, and rubber, which is why we coat our electrical cords with plastic or rubber. Now, still answering that question, when, or getting to the next question, actually, sorry. When does electricity flow? So we talked about why, but when does it flow? Well, in order for electricity to flow, there must be a complete path from the area of greater potential energy to the area of lesser potential energy. Or sometimes I'd like to think of it as a complete path from the positive to the negative. So a complete circuit means that it is an unbroken path. So here, if we look at our battery, you can think of the positive side as the area of greater or high potential energy, and the negative side as the area of less or low potential energy. And so if you have a complete path from one to the other, electricity will flow from one side of the battery to the other. And if you happen to put a light bulb in it, then you can now cause that light bulb to light up because electricity will flow through that device. So the more accurate way to say all of that is complete circuits have an unbroken path from an area of high voltage to an area of low voltage, because remember, voltage is representing our potential energy here. Now, if you have a circuit that doesn't have a complete path, no electricity flows. So it's kind of a unique or a difference between kind of water analogies in that sort of sense, is that for electricity, it's either kind of in the on position or it's in the off position. There is no kind of like trickle position kind of thing or build up or anything along those lines. So for when we have a complete circuit, that's often called a closed circuit, closed loop, or unbroken. If there is a break in it, we call it a broken circuit, open loop, or just broken. Now, we right here are using kind of some imagery that looks very close to, like, a standard battery and a light bulb. But as we're drawing circuits on our papers and communicating about them, it would take a lot of energy to draw something this detailed every single time. So per usual in physics, we're going to simplify things. We don't expect people to be artists. We're going to use a schematic drawing or a simplified drawing. It's like the difference of using a smiley face with a circle, dot, dot, and like a little smile, as opposed to like trying to draw somebody's actual face. So for comparison, we'll use a short line and a long line like this to represent a battery, where the bigger line represents the positive side or area of greater voltage. We'll use lines very similarly to represent wires. We usually try and keep them straight and do kind of 90-degree bends, not weird like curvy stuff. And a light bulb or a lamp will do a circle with an X through it. Is our symbol or representation for it. Now, those aren't the only things we have schematics for. Here are some other common symbols. Sometimes batteries, if you have like stacked batteries like two together, sometimes we use a little bit longer version of that same symbol. We already showed you what a light bulb symbol is. An LED is a little bit different technology. Even though it produces light, it does it differently, so we have a different symbol for it. And then last but not least, we have things called resistors that literally resist or regulate the flow of electricity within a circuit, and we'll talk more about them later, and they're just a simple rectangle like this. So those are some of our common symbols, and that wraps up this lecture. So for this one, we talked about what is electricity, we talked about why does electricity flow, and then lastly we talked about when does it flow, and introduced you to kind of schematic drawings of sorts. You should have 3 or more bullet points worth of notes and a 1 to 2 sentence summary, and then remember to answer any questions that popped up along the way. Alright, this next lecture is on Ohm's law. So as always, you'll need 3 or more bullet points worth of notes and a 1 to 2 sentence summary. Alright, so last time we talked about how we can represent circuits with this symbology here, where this represents the battery, this little piece right here represents the battery, this represents a wire, and this circle with an X to it represents a lamp or light bulb. Well, this is an example of a simple circuit, where it's just literally a power source, the wires, and then one thing in the middle, usually a resistor, which looks like this, but we often will call one with a light bulb still a simple circuit. Now, resistor regulates the flow of electricity. And in fact, light bulbs often behave much like resistors. So we can say they have a certain resistance, but if we're talking about a resistor specifically, that's different than a light bulb. So it's not giving out light. It's just regulating the flow of things. Now, Ohm's law relates our three terms that we talked about before. This idea of voltage, or the amount of energy for each electron or charge, the idea of current, or the how fast things are flowing, and the idea of resistance, or how hard it is for electricity to flow. Before we get into the relationship between those three things, let's quickly talk about current. We've talked about it before as the flow of charge. Well, that just means how much charge is going by each second. We usually won't be using this equation much in this class, but it's here just in case. So if I said there was 10 coulombs of charge that flowed through in 2 seconds, you would take 10 divided by 2 and get 5 amps would be the answer for that. So moving back into kind of the realm of Ohm's law, let's talk about the purpose of each of these things in the circuit. So we have our simple circuit here. Voltage, usually related to the battery, that kind of represents how much energy is being provided or released, is another way you can think about it, as an electron travels from the positive side of the battery to the negative side. Current is talking about the flow, so how much or how fast that charge is flowing. And then lastly, resistance is kind of how hard it is for that electricity to flow. So kind of recapping those things in context here. Here's an analogy in the form of a cartoon to help represent those things. So voltage, often thought of as kind of like the pressure pushing something through. Current is kind of the thing that's actually being moved or flowing. And then resistance, here represented by our Ohm cowboy type person, is kind of how hard is it for that electricity or currents to flow through. Here's the other example with a monkey blowing air through a straw. We've got the idea that the pressure provided by the monkey's lips or cheeks is kind of the voltage. The current is like how fast the air is flowing through, and the resistance would be how much his friend here is squeezing the straw. So obviously without any squeezing, it flows really fast. With squeezing or more resistance, it's harder to flow. So those are some analogies that kind of help people get a sense of it, but ultimately Ohm's law is just this: voltage equals current times resistance. Now there's some caveats to this that you would talk about at an IB level, but for now we will just assume the resistance stays constant, and so therefore Ohm's law applies. So the variables for Ohm's law: V is for the voltage, I is for current, and R is for resistance. Voltage is obviously measured in volts, current is measured in amps, and resistance is measured in ohms. And we use this little omega symbol. It looks like an upside down horseshoe to represent the ohms, just like we use V for volts. So essentially Ohm's law allows you to predict how much current will flow through a circuit for a given voltage. This is useful because you don't want to have to build circuits and then test them after you've built them. You want to know kind of and predict what the effects are going to be when you build it ahead of time. So by using Ohm's law, if we had, let's say, a 10-volt battery connected to a 20-ohm resistor, we could predict that it's going to be 0.5 amps of current flowing through by plugging in the 10 volts and the 20 ohms, and then solving and getting that I, or current, equals 0.5. That's it for Ohm's law. Short but simple. 3 more bullet points worth of notes, please. 1 to 2 sentence summary, and please make sure you've answered any questions that pop up along the way through Edpuzzle or any other platform. Welcome back. This lecture is on power. As always, you need 3 or more bullet points worth of notes and a 1 to 2 sentence summary, and to do any of those questions that pop up through Edpuzzle or any other platform. So we've talked a little bit about voltage before, this idea of the amount of energy of each electron as it kind of moves through a circuit. So if voltage is already talking about the energy per an electron available, then what is power? Because they're going to be different terms, related but different. So power actually ends up being how much energy is used or produced each second. So instead of tracking how much energy each electron has, power just looks at how much total energy is being delivered or transformed or used or produced each second. Now, I don't like using the word used for energy or for power, so we're going to say transformed each second because that's actually what's going on. The energy doesn't disappear, it just changes from one type to another. So power is measured in watts. So when we look at a light bulb, a 100-watt light bulb is more powerful because it literally transforms more electric energy into light energy each second. And that's all that wattage really represents, is how much energy is being transformed each second. If we looked at speakers, for example, this might be a 3-watt speaker versus 3,000 plus watt speaker. It literally just means, oh yeah, it's turning more electrical energy into sound energy each second by having a bigger wattage or more power. Now, power, we may have introduced it before, but it's often thought of as the change in energy per time. So you just take change in energy divided by the change in time that it occurred for, and that's power. And so that's usually how we think about it in this class, even though that's not an official equation. But with circuits, we actually have some things that we can use to calculate power a little bit simpler. Namely, we can just take current times voltage. So power is going to equal just simply the current through the circuit times the voltage, and that gives you how many watts or power that's being produced, or how much energy is being transformed each second. Now, in case you're wondering how it works out that current times voltage actually equals energy per second, we can actually walk through that right now. So before in a previous lecture, we talked about current being charge per time and voltage being energy per charge. Well, if you're doing power equals current times voltage, you can plug those two things in. So we get charge over time times energy over charge. And then just kind of like how in either fractions or chemistry where you cross things out that cancel, since charge is both on the top and the bottom, they cancel each other out, and what that leaves us with is energy divided by time. So it ends up being that current times voltage is actually just giving us energy per time. And the way to think about that is, if current is how many charges come through each second, and voltage is how much energy each electron has, then combining those two things gives you how much energy happens per second. That's it for this one. 3 or more bullet points worth of notes and a 1 to 2 sentence summary, please, and answer any questions that popped up through Edpuzzle or another platform. Welcome back. Let's go ahead and get started with this next lecture. This one is on Kirchhoff's laws. As always, you need 3 or more bullet points worth of notes, a 1 to 2 sentence summary, and to do any of the questions that are embedded in Edpuzzle or any other platform we're using. Alright, so before we've been talking about simple circuits, circuits with just one resistor. This time we're going to start talking about circuits where we have 2 resistors. So let's start with this one, where we have 2 20 ohm resistors, and there are 2 different pathways through the circuit, so they're not on the same pathway. What do you think happens when there are 2 paths? How much current takes each path? So if we have 1 amp of current coming out of the battery, how much goes across this top path versus across this bottom path? And then how much current comes back into the battery on the other side? Go ahead and pause for a second, think about it. Alright, let's begin to walk through it. So charge is conserved. So much like how mass is conserved and energy is conserved, and what I mean by conserved is the total you have before is the total you have after. So like with mass, if I have 1 kilogram clump of clay and a 0.5 kilogram clump of clay, when I smash them together, I'm going to get a 1.5 kilogram clump of clay. So we got this idea that it doesn't change. So charge is conserved. The total amount of charge does not change. And since current is basically just made up of charge, that means current is also conserved. So as we watch our current travel through our circuit here, what happens is the total amount leaving this little junction right here actually stays the same. Now it splits 0.5 and 0.5, but we can see that that adds up to the 1 that was there before. So think about, okay, so then what happens on this other side? How much current do we have reaching there? Well, the answer to that one is that as we reach this junction, the 0.5 and 0.5 add back up, and then we have a total of 1 amp of current coming out the other side and going into the battery. So what that means is all the current that leaves the battery eventually reaches the other side of the battery, and the total amount of current is staying the same. Now that's actually a really cool piece that can be used in your households. If you have any of those electrical outlets that are GFCI, so they have the little reset button on them, it actually uses that idea that the amount of current coming out of one side of your electrical outlet should equal the amount of current going into the other side, and if they ever don't equal, it shuts it off to protect whoever's touching it and having current flow through them and into the ground instead of into the actual electrical outlet. But that's an aside. So going back to our main point, we've got this idea that the amount of current coming out of the battery equals the amount of current coming into the battery, and when there's a split, it just splits, in this case, evenly because it's two equal size resistors. But if we, for example, had two resistors that were different sizes, it would split a little bit different, with more current flowing through the easier pathway of less resistance, and less current flowing through the more challenging pathway, or the pathway of greater resistance. So less open, if that makes sense. So in this one, we have 6 amps coming out, and then it just splits 4-2. So thinking about this idea that the current into a junction equals the current out of a junction, think about what is it going to look like if we have two resistors in a single path. How much current is there, for example, right in between the resistors or on this side? Pause, take a second, think about it. Cool. So hopefully you realize that if we have 1.5 amps of current coming out right here, and there's no other pathway for it to go, then that means 1.5 amps is going to reach right here. And if there's no other pathway, then that means that full 1.5 amps is also going to reach right here, and continue around the circuit and go into the other side. So again, we have 1.5 amps leaving the battery and 1.5 amps coming into the battery, and each resistor gets the full amount of current because they're both on the same pathway. Versus here, they could have different amounts of current because they're on different pathways. So anything on the same pathway gets the same amount of current. Which brings us to the last piece, or not last piece, but the summation of this idea, which is it's Kirchhoff's law, and it's called the junction rule. And more formally, it just says the amount of current going into any node or junction must equal the total amount of current coming out of that node or junction. If there is no split, then obviously it just kind of continues on. So here we have 4 going in and 4 coming out. And here we have 10 going in and 10 coming out. All right, so we've talked about what happens to current when we have only one pathway. What do you think happens to voltage when we only have one pathway? Go ahead and pause, think about it, and you can put your pencil down for right now because I'm just going to have you listen for the next bit. Okay, so like I said, pencils down, stop typing, just listen while I tell you or explain this because it's a little bit more confusing and less intuitive, and I'll have you pick up your pencils and start taking notes at the end of it when I recap. So if we're thinking about voltage, remember that voltage is the amount of energy per unit charge. So what that means is if we're looking at the difference between these two sides of the battery, what that really is saying is if this is a 12-volt battery, there's a difference of 12 volts or 12 levels of energy, if you want to think about it, between one side of the battery and the other. So as current goes around that loop, it's going to lose that much energy, that 12. If this were a 16-volt battery, it would drop or lose 16 volts as it goes around the loop. So if we imagine our current kind of traveling around just one unit of current, we said that what this means with this being a 12-volt battery is that it's going to drop 12 volts as it goes from one side of the battery to the other, which means it'll give off or release 12 joules of energy for each unit of charge, more formally is the way to say that, as it goes from the positive side of the battery to the negative side, which means that each of these resistors can't get a full 12 volts because that would add up to 24 and we'd be like magically creating energy out of nowhere. So what happens is they're going to split the 12 volts or split the energy drops, where the smaller resistor is going to cause a smaller energy drop and the bigger resistor is going to cause a bigger energy drop or voltage drop. So in this case, using V equals IR, we could actually figure out that the voltage drop across the first resistor is going to be 3 volts in this case, and that's after you've calculated current. You can figure that one out. And then if that first one is 3 volt drop, then that means the second one should be a 9 volt drop. So again, the bigger resistor gets a bigger voltage drop or causes a bigger voltage drop. And since they're on the same loop, it should be proportional. So since this is 3 times as big, it should cause 3 times the voltage drop. Another way to think about this is kind of in a water analogy again, where you imagine going from one side of the battery to the other side of the battery as being that 12 volt drop. And with a smaller resistor, that's like a smaller energy drop or energy change. And with the bigger resistor, that is a bigger cliff or energy drop or energy change in this case. All right, so we're going to recap, so now's the time to write. So pick up your pencils and let's go through it. So more formally, what happens is as we go through a loop, current goes through, there's only one pathway. Bigger resistors on that pathway cause a bigger voltage drop. Smaller resistors or smaller resistances cause a smaller voltage drop. But regardless, the combo of those two on this loop must add up to the voltage provided by the battery, because literally if it's providing it, this is what's causing it to drop, and so that's what's going on there. Alright, so now we're going to think about multiple pathways. So we have that same 12 volt battery, but now we have 2 different resistors. Specifically, we've changed the resistances here. This is that scenario we had before where this is 4 amps and 2 amps going through, and what we're going to be looking at is what happens when there are multiple pathways with regards to voltage. We already know current splits. So we can think of this as 2 separate loops, almost independent loops that just happen to be connected to the same battery. So here, as the current going through the circuit following the orange path, let's say, goes through this loop, we know that there is a voltage drop of 12 volts going from the positive side of the battery by the time the current reaches the negative side of the battery. Well, if the only thing in the middle is our 3 ohm resistor, then that gets the entire voltage drop. Now, one thing I haven't mentioned with all this is we are assuming that there is no resistance in the wires. But that is usually a foregone conclusion, or sorry, a foregone assumption that we usually make, kind of like other assumptions around gravity and things along those lines. So in this case, we have that the only thing in the pathway is this 3 ohm resistor, and the only thing on the path of the red pathway is this 6 ohm resistor. So as current goes through, all of the voltage drop occurs over each of these resistors, which means they both get the full 12 volts, which is why I said it's almost like they're on 2 separate circuits that just happen to be connected to the same battery. So obviously the battery will drain a little bit quicker, but each of them is independent of the other. So like I said, this one gets a 12 volt drop and this one gets a 12 volt drop. One analogy we can think of this as if we have a river and a waterfall, so going back to that analogy, almost as if there is a small pathway that some of the water can take. Each amount of water takes the same drop, but obviously less current will go through the one with the bigger resistance, and more current will go through the more open one with less resistance, but both of them are getting the same voltage drop. I mentioned this, but this is kind of how I often will think about what we'll eventually call a parallel circuit. This is effectively the same as if we had each of these resistors connected to a separate battery. Now, they happen to be connected to the same battery, but those loops are basically independent, assuming nothing happens kind of while they're joined together, and they don't affect each other. So formally, this is called Kirchoff's voltage law, also called the loop rule, and it basically says the since voltage is energy, the sum of the voltage gain, they call it EMF. You can learn about that in IB physics. But the sum of the voltage gain, or the voltage provided by the battery, must equal the total voltage drop that happens in a single loop. So as you go from one side of the battery to the other side of the battery, the voltage gain provided by the battery must equal the voltage drop across all of the things on that loop. Which means if you have separate loops, you get a full 12 volt drop on each of those loops. That's it for this one. 3 or more bullet points worth of notes, 1 to 2 sentence summary, and please do any of the embedded questions or questions that are attached to this through Edpuzzle or other platforms. Alright, so we're going to go ahead and get started with the, I believe, last lecture in this series, called Series and Parallel Circuits. So this is really just going to be a recap of some of the things we've already talked about, but in a more formal way. As always, 3 more bullet points worth of notes and a 1 to 2 sentence summary at the end, and do any of the questions that are embedded or attached to this video. So a little bit of a review. When 2 resistors are in a row, the bigger resistor causes a bigger voltage drop. But remember, since they're both on the same loop, the total voltage drop must add up to whatever is being provided by the battery. Also, since they're on the same loop, there's no other place for current to go. And so that means that each resistor gets the same amount of current, or in this case 1.5 amps. This type of circuit where we have one resistor and then another possibly, or even more, is called a series circuit because the resistors are in series. So think about like the World Series or a TV series. It's one game and then another game and then another game, or a TV series would be one episode, another episode, and another episode, all kind of in the same pathway. Now, these resistors, we already talked about it, they will get the same current anytime they're in series for the chunk that is in series, so it doesn't always have to be the whole circuit. And then the resistors in series, or light bulbs, or whatever it is, will each cause a piece of the total voltage drop, so they kind of share the total voltage drop for that loop. So in series, I like to think of it as the current stays the same through the series part, but the voltage is different for each of the resistors or objects in the series. Now, when we're trying to calculate the total resistance of series, it's actually pretty easy. So for example, if we have a 2 ohm and a 6 ohm resistor in series, it actually just adds up to 8 ohms. And so we can use that total or equivalent resistance to do a simplified calculation. So for example, we can figure out that it's 1.5 amps by taking that total resistance and that 12 volts. So the equivalent resistance in series is going to be calculated by simply just adding up all the resistor values, or if there's a light bulb, the resistance of the light bulb, or things along those lines. Now, REQ stands for equivalent resistance here, and what we mean by equivalent is something that is equal to or basically the same as. I like to think of it, for example, as if you had $1 or 4 quarters, they are equivalent. Now, sometimes it might be more helpful to have a single dollar bill. Sometimes it might be more helpful to have 4 quarters, depending on what you're doing in the scenario. Similarly, sometimes it's more useful to just have a single 8 ohm resistor, and sometimes it's more useful to have it broken apart into like a 2 and a 6, or a 4 and a 4, or a 4 2s, or something along those lines. Alright, so that was series. Let's talk about when we have multiple pathways. So here, remember, going over review a little bit, when we have multiple pathways, the total current into a junction splits, and so each resistor gets some of the total current, and then it combines back to be 6 amps at the very end. So here, when they split, each pathway can get different amounts of current based on the size of the resistor. But the voltage drop is the same because each of them is only on a loop with the battery and that one resistor, or whatever else is on that loop causes that full 12 volt drop, versus whatever is on the other loop causes a full 12 volt drop, and they don't affect each other in any way, shape, or form. So they both get the total voltage. This is called a parallel circuit. So an easy way to remember this, you might just memorize it, is in parallel, things in parallel get the same voltage or cause the same voltage drop. But each of them receives a piece of the current flow, and it can be different amounts of current. So if you want things to have different voltages, you want to put them in series, and you can cause different voltage drops. If you want things to have different currents, you want to put them in parallel, and obviously you can kind of combine those two to make more complicated things. But to recap, that is parallel, where each thing gets the same voltage drop, but they will have possibly different current flows based on the resistance. Now, the total resistance or equivalent resistance, meaning like if we were trying to replace this 3 ohm and 6 ohm resistor with just a single resistor that basically allowed the same amount of current, the 6 amps, to flow through, we actually have to use this kind of complicated formula where it's 1 over the equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. Now, or any of the other ones. So what that means is you add up all of the inverses, and then you have to remember to take the reciprocal at the very end, because this isn't equivalent resistance, it's 1 over the equivalent resistance. Now, the reason why this happens is really because if you think about adding a new resistor in parallel, it actually opens up a new pathway for current to flow. So more current is flowing out of the battery. If you remember me talking about it as almost a separate circuit in and of itself. So by allowing more current, that is effectively the same as having less resistance. So one thing that's going to happen is as you add more resistors in parallel, it will actually decrease the total resistance. All right, so to recap, series and parallel are two different styles of circuits. It can be with light bulbs. It could also be with resistors, or a combo of the two. We just refer to it as like a series setup or a parallel setup, and they can be drawn in different ways. With voltage in series, each one causes some of the total voltage drop, so you can add the voltage drop across each light bulb up, and it will equal the total provided by the battery or power source. In parallel, each one gets the same voltage drop. If it's the only thing on the loop, then it gets the full voltage drop of the battery. If there's something else on that loop, then you're combining both series and parallel, and it gets a little bit more complicated, but similar idea. Current, on the other hand, when you're in series, since there's only one loop or one pathway through, everything on the same loop must have the same current. So in this case, we get that the total current is equal to the current through each of those separate light bulbs, or it's the same everywhere. When you have multiple pathways, you have the ability to have more current on one pathway than you do on the other, so the current splits, where it adds up to the total. So notice it's kind of a nice mirror image here, where with series, the current is staying the same, with parallel, the voltage is staying the same, but for each of them, the thing that doesn't stay the same adds up. Now, resistance is this thing that's a little bit funky. Here, with series, it just adds up because it's simple, but with parallel, it's a little bit more complicated with that 1 over equivalent resistance equals 1 over R1 plus 1 over R2. All right, that's it for this one. 3 or more bullet points worth of notes and a 1 to 2 sentence summary, and do any of those embedded questions.